Welcome to week 4 of Math 320. Having gotten an understanding of what the real numbers are in the previous 3 weeks, we now start talking about structures built on top of the real numbers. In the next several weeks, we will be focusing our attention on sequences. You probably have already seen the notion of sequences in calculus 2. Back then, you probably played pretty fast and loose with how you showed a sequence has a limit. The goal of this week is to rectify that. We will start this week by defining the notion of sequences and their limits. We will spend some time exploring some examples. Then, we will talk about some properties or limits of sequences. Starting this week, we will also be following more closely your textbook. For this lecture, you should refer to pages 33 through 38 of your textbook for further exploration. The textbook also offers some different explanation of the same concepts, and feel free to take a look there to seek other points of view on the subject. Okay, let's get started. So, what is a sequence? A sequence is just a fancy word for a function whose domain is the natural numbers. In this course, we will only be talking about sequences whose range, or codomain, are the real numbers. Of course, there can be sequences formed of other things. When necessary, we can specify that our sequence is real valued to indicate what sorts of values its terms take. We refer to the output of a sequence as its terms, and we refer to the input of a sequence as its index. Customarily, instead of using the parentheses notation usually used for functions, we use a subscript notation. So we write x sub n instead of x of n for sequences. So x sub 1 would be the term that corresponds to evaluating the function that underlies the sequence at the input 1. We call it also the first term of the sequence. X sub 2 would be the second term. We imagine the natural numbers as having an order, so an earlier term is a term with a smaller index, and the later term is a term with a larger index. This means we should think of a sequence dynamically as something like a dot jumping along the number line. The picture below shows this dynamical picture. Customarily, when we need to speak of the entire sequence, instead of one of its terms, we frequently use the notation where we put x sub n between a pair of parentheses with an exterior subscript n. The exterior subscript n tells us that in the sequence, the variable n should be considered as the index. This is a useful reminder in the situations where there are multiple variable names that appear in the expression inside of the parentheses. If we want to forget that this is a sequence and that some terms come before others, and just focus on what are the set of values that can appear as outputs of the sequence, we will frequently just use the set builder notation using braces. In the picture below, the set of possible outputs are shown in white, while the sequence that is continually progressing is shown in red. As you can see, the sequence can continue to move around even though there are only, in this picture, a fixed number of possible outputs. Here are some examples. In the first example, the sequence, which we remember is just a function from the naturals to the reals, has a formula giving the nth term to be 1 over n squared. By plugging in a few values of n, we can read off the first few terms of this sequence, and they are 1, 1/4, 1/9, 1/16, and 1/25. If we didn't want to name the sequence, we can also just write parentheses 1 over n squared, close parentheses, subscript n, to denote this sequence. In the second example, the sequence has the formula -1 raised to the power n. The first few terms are -1, +1, -1, +1, and so on. Notice that the terms of the sequence need not have distinct values. Values can be repeated over and over again. Different occurrences of the same output are distinguished by their differing place or index. The set of output values of this sequence contains just 2 points, 1 and -1. Do not confuse a sequence with the set of points that appear as its output. Going back to the picture shown on the previous slide, a sequence is dynamic and has a sense of directionality. The set of outputs is static. The third example reinforces this. Here, the sequence has a formula cosine of n pi over 6. The sequence still has infinitely many terms, but only outputs 6 distinct values. As an aside, what are the possible outputs? More examples. On the previous slide, all examples come from nice formulae. But there is no requirement that sequences have nice formulae. Here are some sequences that are perfectly well described, but whose terms are not easy to evaluate. The first one is the sequence of the digits of pi after the decimal place. It goes something like 1415926535897932384626433 and so on. The second one is a recursive definition. We start with the number 4. We form the next term by dividing the previous term by 2 and adding to it the reciprocal of the previous term. So the second term is 2 plus 1/4, which is 9/4. The third term can be found to be 113 over 72. The third sequence is another famous recursive sequence. Fibonacci's sequence starts 1, 1, 2, 3, 5, 8, 13, 21, and so on. From the third term on, it follows a formula that the next term is equal to the sum of the two previous terms. So the third term is formed from the sum of the first two terms, giving 2. And the fifth term is the sum of the third and the fourth, giving 5, and so on. Having said what a sequence is, let us formally define what it means for a sequence to converge. We will explain the idea behind this notion on the next slide after first seeing what a definition looks like. A sequence is said to converge to a value y if, for every positive real number epsilon, we can find an index capital N such that all terms of the sequence with index later than capital N are no more than a distance epsilon away from y. When this happens, we write in notations that the limit as n goes to infinity of x sub n is equal to y. Or sometimes we use the shorthand x sub n goes to y with an arrow pointing from the sequence to the value. Next, we give some commonly used terminology. We use the word convergent as an adjective to refer to the sequence that converges to some number, but suppressing the number to which it converges. And if we want to talk about a number to which the sequence converges, we refer to it as the limit of the sequence. Finally, if a sequence is such that we cannot find any number to which it converges, then we say that the sequence diverges. Let's try to explain the definition a little bit. The intuition is that convergence uses heavily the directionality implicit in the indexing of the terms. One way to think about convergence is to think dynamically. Imagine a sequence is described not only by the set of values it outputs, but by the dot that hops along those values. So the dot starts at the value that is x1, then it jumps to x2, then it jumps to x3, and then x4, and so on. Remembering that the sequence is allowed to repeat values, the dot is allowed to jump back to values previously visited. The notion of convergence describes a process where the dot gets closer and closer to a particular value. Note that the dot doesn't actually have to land on the value. That is, the limit of a sequence doesn't have to appear as a value of the sequence. Also, the process of getting closer to closer doesn't have to be one way. The dot is allowed to occasionally get further away again after coming close. But this backtracking is only allowed within reason. For example, let's watch this animation a little bit. The white dots represent the values that can be taken by the sequence. We don't show all of them and truncate the animation after 50 or so steps, but already you can see that the possible values accumulate near the left end. If you follow the sequence, which is the moving red dot, you see that it moves on the whole toward where things accumulate. But this sequence also illustrates what is meant by backtracking within reason. We see that the sequence gets close to the limiting value, bounces back out again, and moves back in. But each time, the amount of backtracking is smaller and smaller. This guarantees that eventually the sequence will always become very close to the limit point. Let's look at the definition again, now that we've thought about it, about what it should mean. First, let's break down the definitions into small parts. Let's start at the beginning of the second line. The variable epsilon in the definition, it is a measure of closeness. How do we know that? For this, we look at where else the variable epsilon appears. It appears again on the third line as an upper bound for the difference of two numbers. The difference of two numbers captures how far they are apart. So, the variable epsilon is something used to control how far numbers are apart. Coming back to the end of the second line, we see the variable capital N. This is a measure of how far along the sequence we need to go. How do we know that? We look at other place where the variable capital N appears. It appears again at the end of the third line, where we see small n is greater than big N. Now, small n appears in the beginning of the third line as part of the notation x sub n, so we understand that small n is referring to the index of a sequence. And since we are comparing it to big N, the variable big N should be considered as a special index to which we want to compare other indices. And that we only want to think about terms of the sequence that happens later than big N. Next, let's take a look at the logic. The definition has the form, for every something, there exists something else, such that another statement holds. We should remember that in a statement like this, the quantities that are introduced later are allowed to depend on quantities introduced first. So, we are in a situation where the index capital N can and should depend on the distance epsilon. Notice further that within the statement after the such that, there is another whenever. The whenever should be interpreted as another for every. So this definition actually has 3 layers of quantifiers. This complexity is why I am spending some time to dissect it for you. From the logical components, we can now reverse it to form the negation of the definition. In other words, we are now describing what is the definition of the sequence x sub n not converging to the value y. It says that the failure of convergence to y means that we can find a distance epsilon such that no matter how far we go in setting the capital index n, we can find an even later term x sub n that is more than epsilon distance away from the target y. Notice that in forming the negation, we kept the order of the quantifiers but swapped all there exists with for every and vice versa. This should be somewhat familiar from your Intro to Proofs course. Between the definition statement and its negation, we can now look more holistically and see what the definition is saying. Thinking back to the dynamical picture of a dot hopping from value to value, the notion of getting closer and closer in the process of convergence is that of having a point of no return. But notice that this is a point in time, not in space. More precisely, it says that for every threshold distance epsilon we set, there is a point in time given by the index capital N that once we go past that point in time, the dot will no longer be able to escape from the threshold. As one might expect, setting finer and finer threshold distances, we may have to wait longer and longer before the dot settles down and stays within the threshold. In other words, we expect that the smaller epsilon should be compensated by a larger n, at least when we are dealing with a converging sequence. The negation also makes clear what it means by allowing the sequence to backtrack within reason. Backtracking here means for the sequence to make a close approach to the limit and then getting farther again. For a sequence to converge, this means that the longer we wait, the less the amount of backtracking should be allowed. If, no matter how long we wait, the sequence always has the chance of backtracking out past a fixed threshold epsilon, this would make it satisfy the negation of the definition and prove that the sequence does not converge to the proposed limit. This is illustrated by the next animation. Here, we see that a portion of the sequence looks like it wants to move toward the center. But if you pay attention, you will see that every now and then, the sequence always jumps back out to this point on the far left. So even though the rest of the sequence looks like it wants to move toward the middle, the fact that a part of the sequence keeps escaping out to the left means that the center cannot be a limit of the sequence. If you take as an epsilon, that is half the distance between the center and the point on the left, then for any time n, we can find a later time that the sequence comes back out to the left. And at that instance, the distance between the term x sub small n and the center is going to be twice epsilon that we chose. And this shows that the center is not a limit. As a final point, let's use the negation to formalize what needs to be proven in order to demonstrate that a sequence diverges. Since divergence means that for every target value y, the negation of the convergence statement is true, we can summarize the definition of a sequence to diverge as a sentence with 4 levels of quantifiers. For every real value y, there exists a distance threshold epsilon such that for every index capital N, we can find an even later index small n, and the term x sub n corresponding to this later index is more than epsilon distance away from the target y. For your convenience, the formal definitions of convergence and divergence will be given on the usable statements sheet. We will stop here for this lecture. It's very few slides, but a lot to digest. On this slide, I show the LaTeX notations for some of the symbols used in this lecture, for those of you preparing homework using LaTeX. A reminder, these are all mathematical symbols, so they should be enclosed in dollar signs when you type them in LaTeX. Next lecture, we will discuss a bit more how to prove or disprove the convergence of a sequence and give some examples. See you later.